Every time you open a website, your browser fires an HTTP request. That request carries not just a URL, but a bundle of headers encoding routing decisions, authentication credentials, cache directives, and security parameters. In modern architectures, this single request traverses a chain of proxies, load balancers, WAF, and application servers, each one inspecting, rewriting, or discarding headers before passing the request along. This makes HTTP headers the single largest attack surface in web applications. The standard defense is the Web Application Firewall, or WAF, which matches incoming requests against a library of static rules. But attackers have learned to mutate their payloads, using encoding tricks, structural ambiguities, and protocol edge cases that slip past rigid pattern matching. The result is an arms race where every new evasion technique demands a new handwritten rule. And in many production environments, you simply do not have labeled attack samples to train a supervised classifier. You only have normal traffic. So the question becomes, can we learn what normal HTTP traffic looks like, well enough to flag anything that deviates? Neuralshield's answer starts with a key observation about how HTTP is structured. HTTP has a built-in duality. There is the syntactic dimension, the raw textual form of the request, its line structure, delimiters, header names, encoding choices, and byte-level formatting. And then there is the semantic dimension, what that request actually means when processed, the routing decisions it triggers, the authentication it claims, the resources it accesses. The key insight is that in legitimate traffic, these two dimensions are tightly aligned. A well-formed request looks normal and means something normal. But in malicious traffic, that correspondence breaks down. Consider HTTP request smuggling. Two servers in a chain disagree on where one request ends and the next begins, because content length and transfer encoding headers provide contradictory framing signals. The syntax is ambiguous, and different components derive different semantics from the same bytes. Or take CRLF injection, where an attacker embeds new line sequences inside a header value, causing a downstream parser to interpret data as a new header entirely. The form of the message and its effective meaning diverge. Neuralshield is built around the idea that if you can capture both dimensions independently, you can detect anomalies that either view alone would miss. But before you can build detectors, you need to know what to look for. What do structural anomalies actually look like in an HTTP packet? Neuralshield proposes a taxonomy of 5 families of structural anomalies in HTTP requests. The grouping criterion is purely observational. How does the anomaly manifest in the byte stream, regardless of which vulnerability it exploits or what impact it produces? Two conceptually different attacks that look the same on the wire belong to the same family. The first family is duplication, conflict, and selection ambiguity. The packet contains redundant or contradictory information where there should be a single authoritative value. Think duplicate host headers with different domains or content length coexisting with transfer encoding. The second family is injection of structural delimiters. Data that should be content gets interpreted as protocol-level separators, like embedded CRLF sequences or OBS-fold continuation lines. The third is encoding and character repertoire anomalies, double percent encoding, full-width Unicode characters, or mixed scripts within a single token. The fourth targets the request target structure itself, path traversal segments, consecutive slashes, mixed query delimiters. And the fifth covers statistical outliers, syntactically valid fields whose magnitudes fall far outside the normal distribution, like a content length of 100 megabytes or 48 custom headers. These 5 families become the design target for the preprocessing pipeline. The goal is to normalize legitimate traffic into a stable canonical form while exposing these structural deviations as explicit signals. The preprocessing pipeline takes a raw HTTP request and transforms it through 12 deterministic steps, organized in 3 phases. The first phase handles framing and structuring, cleaning BOM markers, splitting the request into labeled sections like method, URL, query, and headers, and resolving OBS-fold continuations. The second phase performs normalization and flag extraction, validating header names, detecting duplicates and hop-by-hop headers, collapsing anomalous whitespace, flagging dangerous characters and mixed scripts, reconstructing the absolute URL, and classifying Unicode anomalies. The third phase handles canonical serialization, detecting percent encoding tricks, HTML entities, query parameter anomalies, and path structure irregularities. Two design principles are critical here. First, idempotence. Applying the pipeline twice produces the same output as applying it once, so legitimate requests that are already well-formed pass through unchanged. Second, non-destructiveness. The pipeline never rewrites suspicious content. Instead, it annotates it with flags. If a header value contains embedded CRLF sequences, the original bytes are preserved and a badcalf flag is attached. This means the downstream representations see both the normalized structure and the evidence of anomalies, without losing any information. To give you a feel for the concrete steps, framing cleanup strips byte order marks and trims control characters. Request structure splits the request line and validates the method and HTTP version. Header unfold obs fold detects obsolete line folding. Header normalization duplicates catches in valid header names, duplicates, and hop-by-hop headers. Whitespace collapse flags anomalous padding. Dangerous characters script mixing scans for injection characters and mixed alphabets. Absolute URL Builder reconstructs the canonical URL and validates the host. Unicode NFKC and control classifies Unicode anomalies without rewriting the text. Percent decode once detects double encoding and dangerous percent sequences. HTML entity decode once spots HTML entities in URL contexts. Query parser and flags canonizes parameters and flags repeated keys. And path structure normalizer catches traversal patterns and redundant slashes. Once the pipeline has produced a canonical, flag-annotated representation of each request, Neuralshield builds two complementary views on top of it. The syntactic view treats each preprocessed request as a document. It concatenates the canonical elements, method, URL, query parameters, headers, and structural flags into a single text sequence. This corpus is then transformed through TF-IDF, which captures the lexical regularities of normal traffic, which tokens appear, how often, and in what combinations. PCA reduces the resulting high-dimensional sparse vectors into a compact representation that preserves the dominant variance directions. The key property of this view is that it operates purely on form. It sees the textual shape of the request without interpreting what any field means. The semantic view takes a fundamentally different approach. Each preprocessed request is linearized into a token sequence and fed to SecBERT, a BERT model pre-trained on cybersecurity text including threat reports, logs, and alert data. The CLS token embedding produces a 768-dimensional dense vector that captures the functional meaning of the request, the contextual relationships between its method, path, headers, and parameter values. Where the syntactic view asks how does this request look, the semantic view asks what does this request mean. Three encoding variants are explored: a base version using the pre-trained CLS embedding directly, an adapted version with fine-tuned weights and pooling over the last two hidden layers, and a flag-weighted variant that upweights tokens associated with structural anomaly flags. Each view now produces a vector space where normal traffic should cluster tightly. The question is how to detect outliers in each space and then combine the evidence. For the syntactic view, Neuralshield uses local outlier factor, or LOF. LOF measures how isolated a point is relative to its nearest neighbors. It fits on the TF-IDF plus PCA vectors of legitimate traffic only, learning the local density structure of normal requests. At inference time, a request whose syntactic representation falls in a sparse region gets a high anomaly score. The intuition is that unusual token combinations, unexpected flags, or rare structural patterns will land far from the normal density mass. For the semantic view, the detector is the Mahalanobis distance. It estimates the mean and covariance matrix of the SecBERT embeddings from legitimate traffic, then measures how far each new request falls from that centroid, weighted by the covariance structure. This is well suited to the dense embedding space because SecBERT representations tend to cluster in an approximately ellipsoidal region. The Mahalanobis distance naturally accounts for correlations between embedding dimensions, so it detects unusual combinations even when individual dimensions look normal. The two detector scores operate on different scales, so they are first z-score normalized using the statistics of the legitimate validation set. Then they are combined through a weighted linear fusion. The final score equals W times the normalized LOF score plus 1 minus W times the normalized Mahalanobis score, where W is a weight between 0 and 1. A threshold on this fused score determines the final binary decision. The weight W is selected empirically per dataset by maximizing AUC on a validation split, while holding the false positive rate at 5%. That is the full architecture. Now let's see what happens when we test it. The evaluation uses 3 benchmark datasets chosen for their diversity. CSIC 2010 is synthetic e-commerce traffic with about 72,000 normal and 25,000 anomalous requests, covering SQL injection, XSS, path traversal, and CRLF attacks. SRBH 2020 comes from a real WordPress honeypot with over 900,000 requests and multi-label CAPIC attack categories. And PKDD 2007 contains roughly 50,000 requests from a real web agency, with 7 attack categories and a realistic noise dimension where about 10% of attacks are syntactically malicious but directed at non-existent resources. All experiments use a strict one-class protocol. Only normal traffic for training, a normal validation split for tuning, and a mixed test set for evaluation. The first experiment isolates the impact of the preprocessing pipeline. 6 different encoder-detector combinations are evaluated on CSIC 2010, each tested with and without the structural preprocessing. The results are striking. Every single configuration improves after preprocessing. The largest gain is +0. 283 AUC for TF-IDF with PCA and Mahalanobis, jumping from 0. 504 to 0. 787. Even dense pre-trained models like by T5 and SecBERT gain between 0, 0.2 and 0, 0.9 awk. The score distribution plots show the mechanism clearly. Preprocessing compresses the normal traffic distribution while pushing attack scores further away, widening the gap between classes and making threshold calibration much easier. The second experiment tests whether the 2 views truly capture different aspects of anomalies. Across all 3 datasets, the syntactic detector based on TF-IDF plus LOF and the semantic detector based on SecBERT plus Mahalanobis show low Pearson correlation between 0, 17 and 0, 33, and low Jaccard overlap of their detection sets between 0, 13 and 0, 36. Their agreement rate is moderate, around 71 to 77%. This means each view catches a substantial number of attacks that the other misses. The syntactic view is more sensitive to structural irregularities like encoding tricks and header conflicts, while the semantic view picks up anomalies in the functional context of the request. The ensemble combines both perspectives and outperforms each individual detector on every dataset. On CSIC 2010 with an optimal weight of 0, 75 favoring the syntactic view, the ensemble achieves 0, 861 awk, a 12% relative improvement over the best individual model. On PKDD 2007 with weight 0, 2 favoring the semantic view, it reaches 0, 780. And on SRBH 2020 with weight 0, 6, it hits 0, 928, a 6% improvement. The optimal weight varies by dataset because the attack composition differs. CSIC 2010 is dominated by structurally visible attacks like SQL injection and XSS, so the syntactic view gets more weight. PKDD 2007 has subtler, more heterogeneous attacks, where the semantic view contributes more. These are promising results, but they come with important caveats. The 3 benchmark datasets, while widely used, may not reflect contemporary attack patterns. CSIC 2010 is fully synthetic, and the real-world datasets are from 2007 and 2020. The evaluation uses aggregate metrics like AUC and recall at fixed FPR, without breaking down performance by attack type, so it remains unclear which specific threat families each view handles best or worst. The ensemble weight is selected by exhaustive search over the validation set of each dataset, which would not be feasible in a real deployment without knowledge of the attack distribution. And the entire framework is limited to HTTP/1. 1. The text-based protocol version, leaving HTTP/2 and HTTP/3 binary framing as open territory. Let's bring it together. Neuralshield starts from the observation that HTTP has a syntactic-semantic duality that attackers exploit and existing defenses ignore. It formalizes 5 families of structural anomalies, builds a 12-step preprocessing pipeline that normalizes legitimate traffic while preserving anomaly evidence, and constructs 2 complementary views: a syntactic one using TF-IDF, PCA, and LOF, and a semantic one using SecBERT and Mahalanobis distance. The preprocessing alone improves every tested model. The 2 views capture genuinely different dimensions of anomalies, and the weighted fusion ensemble outperforms both individual detectors across 3 diverse benchmarks. The deeper lesson here is about representation design. Rather than building a single monolithic detector, Neuralshield decomposes the problem along a natural axis of the protocol itself: form versus meaning. Each axis gets the representation and detector best suited to its statistical structure. And the preprocessing layer, which might seem like just a boring data cleaning step, turns out to be the single most impactful component, reshaping the geometry of the representation space in ways that every downstream model benefits from. For anyone working on anomaly detection in structured protocols, that is a design pattern worth